Okay, students, so we are on section 1.1, and we have gone over, let me scroll up here, we've gone over a fair number of problems in this section on rates and limits. Example 1 through 4, 5, let me see, 4 and 5. We ended with that example 5 problem where we were taking the limit and we were using the theorem where the limit of sine x over x is equal to 1. So doing a little manipulation and proving it mathematically. Now we can obtain a limit numerically using our calculators, but there are times where we are called on to actually use a theorem or some other method, algebraic method, to find the limit. So a couple things about this. Remember the right hand, we have one-sided and two-sided limits, and sometimes we need to distinguish what happens to the function just to the right of c and to the left. To do this, we call the limit of f of x as it approaches c from the right-hand limit, and from the left-hand limit of f at c. The notation, we use a little plus after the c for the right-hand limit and a minus after the c for the left-hand limit, both superscripted. So if you're looking at a number line here, I just wanted to zoom in on this. So if we look at c in the middle, and then on the left we have the limit of f of x as x approaches c from the left. So we're talking about what happens as the x values move in towards c from the left, and then from the right, you can see where we have the limit as x approaches c from the right, we put a little plus sign there then. So just looking at that notation. So sometimes it's different. Now, when I gave you that diagram and we were talking about directions of route 50 and 92, it kind of makes sense. You don't, if I said, hey, take 92 and then make a right turn at 50, well, which 92 are you talking about? So what we mean by left and right hand limits, there are times where it could be different and therefore the limit does not exist. So keep that in mind, and we have an example like that. I'm just going to go through these pretty quickly, but to do a numerical analysis, there are times where if we're taking the limit as x approaches 1, c is equal to 1, we might pick numbers very close, like very close to 1, such as 0.999 or 1.001, to get a good idea what's going on. And when you have a calculator, that kind of helps out, especially if maybe the algebraic method is failing you. Okay, so remember that a limit, if I have this next example where I'm taking the limit as x approaches 2. Now I have a lot of writing on here, so I want to kind of limit it. So when we take this limit, we end up getting 7 over 0. Now, what I did in class today is I took, let me zoom in here on this one. I don't know if I can zoom in too much. Students kind of wondered, what is 7 divided by 0? So if you see what the idea is, if you divide 7 by numbers that get closer and closer to 0, we get a huge number, right? So 7 divided by 0 is either plus or minus infinity. And then the thing about 0 could be either positive or negative, depending, if you look, here's 0, right? If you're coming in this way, you'd be approaching a negative 0. If you're coming in this way, you'd be approaching a positive 0. So you've never really thought about that. You've kind of always assumed that 0 was 0, nothing else. But when we're talking about infinitesimal distances, we now have a sign that we assign to 0. So if we take this limit and we say that it exists, this is what we mean from the left-hand side and from the right-hand side. So if we look at these both, the left-hand side, we'd have that little minus sign, right? So, and then on the right-hand side, we have the little plus sign, right, of the function. Now, I'm going to leave it up to you to look at a graph of this, but what I'm going to do is I'm going to zoom in over here and say, if I take this function and up here, see how I pick some numbers out? Let me erase this here and take this up. I'm talking about the two sides. I hope that's all right there. So the two sides of 2, left and right. So on the left, I picked 1.99, and see the function is x cubed minus 1 and over x minus 2, right? So you can see I'm putting the x value of, here's my x of left, if you will. it's 1.99, and my x on the right is then going to be 2.001. You can see now, you don't really have to do any math with this other than the fact that at the top, it's 7. It's maybe around 7, but it doesn't really matter for our purposes. We're looking at the denominator, and we want to find out what kind of zero it is. So if I put in 1.99, missing a decimal place there, 1.99 minus 2, it's going to be a negative 0. Okay, it's coming on and then if I put in a 2.001 on the right-hand side, it's going to be a positive 0. So that'll give you the two answers. On the left, your limit's going to approach negative infinity. On the right, infinity. Sometimes you won't have a graphing calculator, and that's a really easy way to determine what your asymptotes are going to be, or what is going to happen at your asymptotes. So you can see on the left-hand side, the function is going to, the limit is going to be negative infinity on the left-hand side. On the right-hand side, the function is going to go to positive infinity at that vertical asymptote. So what we're going to say, infinity is not a limit. It's just an idea of unboundedness. So there is no limit. Like a speed limit, hey, you can't go faster than 65. Maybe they'll allow for a little bit more, but that's a limit. So the limit in this case then does not exist. So at the AP College Board, we kind of look at the fact that we want you to qualify the limit. We don't want you to say does not exist. And we have talked about a graph like the next one, and there are a couple ways that a limit does not exist. And one of them is that there's no graph there, or on one side or the other. Another one is that the graph bounds, it tends towards infinity or negative infinity, so the limit doesn't exist. The other one is when the left isn't equal to the right. So that's what this one is about. So remember this, you had the graph of the greatest integer function, and you see those brackets that look like this. There's kind of a single line there like this, right? In your calculator, you can put this in your calculator as y is equal to, and once you have your cursor there under y1, you're going to go to math, and you're going to go over to number, and I think it's 5 for int. And then you should have this idea y1, or you should have this impression int, and you should have a parenthesis, type in an x there, and then you must close the parenthesis. I'm trying to get you in good habits to always for proper formatting. So notice with your graph, when you look at it, it's a step. It's a series of steps, right? So depending on your mode in your calculator, if it's connected or not connected, or the formatting is set, these should not be connected steps. So what we're doing is we're looking at the limit as x approaches 3 here. It says the greatest integer function, f of x is equal to intx, has different right and left-hand limits. So I chose to look at the limit as x approaches 3 from the left and the right. And you can see from the left, as you're coming in here, your function value is 2. But from the right, as you're coming in, your function value appears to be right here. It's 3. Now remember, it doesn't matter if there's a point there or not. In this case, from the left, you don't have a point, and it looks like there's a hole at the point 3, 2, at the coordinate 3, 2. So because the limit from the left is 2, and get the notation down, and from the right, the limit as x approaches 3 is 3, the limit does not exist if you consider the limit as x approaches 3. This notation we can't use for this, or we could use it, but we have to say that the limit does not exist, and that is because the limit from the left is not equal to the limit from the right, okay? So the last thing that we talk about here, I cover in the videos from example 8 and from example 9, so that will finish your videos for this section on rates of change and limits. Okay, so have a good night, and we'll see you when we see you. This is Alanator out.